Hello, I hope everyone is doing well. Right now, I'm going to do Taylor expansion slash series. I'm going to talk about polynomial equations and why they are easier, how non-polynomials can be roughly equal to polynomials, and this will lead into the Taylor expansion equation, and then its importance and use, and then lead to the expression, when in doubt, Taylor expand. So, first off, we are going to talk a bit about polynomials. Polynomial equations, such as like ax squared, like plus bx plus c, these equations of types. Now, why do we like polynomial equations? Well, for one, they're easier to visualize. For example, this can be an x curve, or for example, we can look at x squared, or for example, something like x cubed. Or these shapes can be pretty easily visualized by the leading power coefficient. Another use is for visualize. Another use is for computing, like for math reasons. It's a lot easier to compute something like this, or something like, or the derivative of something like this. So there's a lot of reasons why we like polynomials. They are easier to visualize, they are easier to compute. So let's talk a bit about non-polynomials. And can we like roughly make them polynomials? Well, for starters, I'm going to show you cosine of x. Cosine of x being this equation, which you probably have seen before. It looks something like this. Not drawn to scale. This is like pi. This is like what, negative pi. Well, we can roughly approximate this around 0 as 1 minus x squared over 2. Cosine of x is a non-polynomial, so it can actually be hard to visualize that in terms, but something like this right here, we know that this is a down-facing polynomial, and if we were to put this in here, this is not drawn to scale, but it pretty much completely overlaps cosine from about the range of negative pi over 2 to x to pi over 2, not including negative pi half and 2 pi half, but in that area. It's a really good approximation. So, and this is around like x equals 0, just around this point right here. So what does this mean though? So we know that we can make cosine about equal to, well, we can polymerize it in a way. I don't know if that's a word, but I'll use it here. So for example, we basically set it up so that it is equal to a polynomial equation, such as this. So we have like our constants, and then we have our variables right here being x, and our constants, c0, c1, c2, are what we're going to use in order to actually fit the curve to this one right here, the cosine curve. And as we keep doing this infinitely, it will keep getting better and better, to the point where it can almost seem identical in a given area. So how do we do? So for this, we need to find C0, we need to find C1, we need to find C2, and we need to continue. We need to find the constants in each of these terms so that we can fit our polynomial equation to our non-polynomial equation. So essentially, we want to find this. We want to find the constant at any given index. So C0, C1, C2, etc. So this is going to lead into our Taylor expansion / series right here. So let's look at the power series. We're trying to get this into a polynomial that follows the power series. So let's look at that first. So we're starting at 0 to infinity. We have some type of constant n, and then we have our variable x to the power n. And this, of course, will be equal to c0 plus c1x plus c2x plus squared, and so on and so forth. So you might be able to see where we are going from here. But just for the fun of it, let's change up this a bit. Let's say that from keeping the same from 0 to infinity, keeping that constant, we want that constant, but we're going to say from x minus a squared, x minus a to the power of n. And then this series would be c0 plus c1, x minus a, plus, c2, x minus a squared, plus so on and so forth. So why did I choose that? Well, because first off, if we have f of a, so we plug in, whatever the constant a is, what is that going to be? Well, it's going to be c0, okay, plus c1 of, now we're going to plug in this a right here, of course, a minus a plus c2 of a minus a squared. What does that mean? It means that these are 0, so we're only looking at right here. So f of a is equal to c0. Okay, so that's interesting. Now let's look at what is the derivative of x. We want to find it around a given point, so let's take the derivative of that point. That might give us a better indication of the function, since the derivative is the change within the slope. Well, let's do this first. So our first term is 0. Why? Because if we take the derivative of a constant, is equal to 0. And then if we take the derivative of this right here, we're just going to get whatever the coefficient is in front. So that is just going to be plus c1 plus, for this term right here, we're going to use the power rule. That will put that 2 out in front, and then that will make that x minus a, and then we take the derivative of this point within here, and that's equal to 1. So we just get 2 times c2 times x minus a, and then so on and so forth. Well, now, since we do have this a in here, let's plug in f prime of a at a. Well, we still have 0 right here, right? And we have c1 right here. But then what do we get when we plug in here? Well, we get 0 right here. So that would mean that f prime of a is just equal to c1. Okay, so that's an interesting point that has just been made. Well, let's continue. Let's take the second derivative. Let's get a little bit more information at that single point and how that slope is doing. Well, we take, if we were looking at here, constant, 0. Right here, take the first derivative, that's going to be equal to 0, so we're just left at 1 right here, so we're just taking of a constant again. Then we're taking the first derivative, since this is one derivative, let's take the derivative again from right here. This is going to be 2c2, okay, and then of course times 1. Then what else? Well, if we look at the c3 variable, we would have a 6 c3. Why? That's because we brought a 3 down times a 2. 2 times 3 is going to be equal to 6. X minus a, plus so on and so forth. Well, now, of course, we want to take f prime of a, as you already know, and we are going to look at, what is that going to be when we plug in a? Well, right here, we know that that's going to be equal to 0, so this is going to be equal to 2 times c2. So there's a pattern going on here. every time we take the derivative, its respective coefficient, whatever is up here, so this is the second derivative, it's the second C2, the coefficient of n, is going to be the only term when we plug a in. And this is going to keep repeating and repeating and repeating. So we see a pattern right here. Well, so let's look at these variables first off. So C0, that's equals f of a. C1, when we plug that in, the derivative, or f prime of a. C2, what happens when we plug that in? Well, we get 1/2, right? Because we're basically pushing this 1/2 over f prime of a. And C3, well, if we were to find C3, we get 1/3 factorial of f prime prime prime. Oh, too many primes. Of a. As for the factorial, what is that? Well, that is just because when we brought this down right here, this was 2 times 3 because we brought down the exponent. Well, we know that 3 factorial is equal to 1 times 2 times 3, which is equal to 6. And this is actually really equal to 1, right? Because that 2 came down before. So time multiplied by 1 is just itself. And we can see that this is repeating because as we bring down the force coefficient, that is going to be equal to 24, and so on and so forth. So this is really just taking the factorial, and that is just because we always bring down the exponent down to become the coefficient, and we multiply what was previously there, which was the previous coefficient that came down to become the coefficient. And then it made, of course, that exponent -1, and it goes, and so on and so forth. So we have a pattern for Cn right here. 1 over the power of n factorial, right? Because whatever this is right here is going to be the factorial of f the power of n right here, right? Because we're looking at the derivatives. So this right here is to the third. The third derivative right now is C3, this right there, as you can see. So this right here are all the same. And so this gives us our coefficient that we were looking for previously when we were trying to find it up here. So that's perfect. So all we need to do is we just plug that in. So we know what our x of x was. That was the 0, n equals 0 of Cn of x minus a n, the exponent of m. So we have Cn, we just plug it in right here. That is going to be equal to the exponent of 0, n equals 0 of 1 over n prime of f the power of n a times x minus a power of n. Look at that. Right there. Now we have the Taylor series. And this is around like the point of x equals a. So that's perfect. Look at that. We have just found the Taylor series. So breaking that down a bit more, let's look at another common one you'll hear is the Maclaurin series. The Maclaurin series is the exact same as the Taylor series, except it's always going to be around x equals 0. So essentially this a is not going to be there. So for the Maclaurin series, that f of x is going to be equal to is just going to be equal to f of n 0, because we're always going to plug in 0, because that will be our a in this case. Power of x, the power of n, be right, because that a is 0. And from there, let's look at that non-polynomial function we looked at oh so long ago, right here. Well, before we were trying to approximate this, or to try to polymerize this, quote unquote. I wonder if that's a word. I hope it is. C2 x squared plus so on so. And yeah, so we have found these coefficients in this Taylor series, and we now can find, if you were to plug this in, you would get this right here. So this is wonderful. Of course, we do want to say that the reason why we use the reason is because we want to be around any point, right? We want to find this not just around 0. Now that's too limiting, of course. So we want to be around any point x. So for example, we could do x equals 1. Maybe that's useful, or so on. So there's a thing I'd like to point out with this. As you know, we've only used the first two terms within cosine of x. Why is that? That is because at small angles, this is all you need to approximate that, right? That is this equation right here. So if you're working within this bounds right here, you only need these first two terms. So this gives us a really interesting term where that new terms, so terms added on, so these terms right here, don't affect the old terms. This is really, really amazing because this allows us to approximate things. So we can say things like, for example, at small angles, sine is equal to theta, which is another Taylor expansion on that at small angles. At small angle right here. But of course, this could be at any point, right? That's why we use that a, so we could plug in at any point along x. And it will give us the approximation within that given area. Will tell us the behavior of that area, right? Because that leads us into the importance of why do we want this, right? Well, of course, one reason is it makes non-polynomial problems easier. You know, we want things to be easy. This is great. But two, we also get derivative information. So we use the derivative, right? Or f of n, I'll just say, of a. Info, at a point to get information around that point. This being the key word, around that point. So from a single point, we can use the properties of a derivative, which is understanding the change of the slope, to understand the area around that slope. I mean, we've heard before about like the critical point, which is, I believe, the second derivative and stuff like that. We are using this in order to better understand this. And that is why, when in doubt, Taylor expand. Taylor expand. When in doubt, Taylor expand. I spelled that wrong. And, of course, because we want to be very cool here and we want to be able to impress our friends when we use the Taylor expansion. So another way that you can write the Taylor expansion is essentially whatever the function is of r. This for r could also be just x. At plus, you give a certain distance. So this epsilon right here could be small or large. And then that is equal to e to the power of epsilon over d dr, or again, that can be x, power to the function of whatever that is at r, or that could be x as well. And in physics, a lot of times you will see things in 3 dimensions. So you'll see things with x, y, and z components, right? Because we live in a 3D world. So for that, you can take the same function, and this is why I used R for this, right here, plus this, right, because we're looking at 3 components. We're looking at x, y, and z within both these components. And this is going to be epsilon. So those 3 components, again, I want to say that is why I'm saying that it is a vector almost. It just has 3, the x, y, and z components, times gradient times f right here. This function, which of course is also 3 components. And this gradient is just d dx, d dy, d dz. So it's really just taking this right here, but 3 times in the x, y, and z direction. So thank you so much for watching. I hope you learned something new about the Taylor expansion and why it is so important. It is a very fundamental equation in physics. It helps computers calculate these non-polynomials. It also helps us understand these non-polynomials, not only by making them easier, but by understanding the behavior or like the limits of this function at a given point. So thank you so much for listening. Let me know if I made any mistakes, and I hope you all have a wonderful